The Nebraska sandhills cut deep in January of 1900 when ice formed on the inside walls of Jonah Miller's cabin despite a fire burning 3 feet from his frozen water bucket. He had built his homestead exactly the way every settler was told to build: tight log walls, thick sod construction, stone fireplace, following decades of proven frontier wisdom. By February, he had burned through 4 cords of wood, and still his family shivered through bitter prairie nights. Across the grasslands, homesteaders were losing the same battle in houses built by the book and failing by degrees. Over the next 2 years, Jonah quietly applied an old technique using the one material everyone said belonged in barns, not homes. His house stayed 30 degrees warmer than log cabins while burning half the wood. What did he understand about heat that every other prairie builder had completely overlooked? The sandhills stretched endlessly under a pale March sky in 1898, rolling grassland broken only by scattered cottonwoods, huddled in creek beds, and the occasional windmill spinning against the horizon. This was not timber country. The nearest railroad depot lay 40 miles east in Broken Bow, and every stick of milled lumber had to be hauled by wagon across sand roads that disappeared in spring storms or summer heat. What grew here was grass, endless waves of it, turning the hills bronze in autumn and hiding the sandy soil that made this country both fertile and treacherous for anyone trying to build a permanent home. The Homestead Act had opened these lands to settlement, promising 160 acres to any family willing to prove up their claim by building a dwelling and farming the ground for 5 years. By the late 1890s, families were scattered across the region like seeds on the wind, each trying to scratch out a living from soil that grew excellent hay but offered little in the way of building materials. The closest thing to local stone lay in creek beds 20 miles apart, and even the hardiest cottonwoods rarely grew thick enough for proper house logs. Most settlers fell back on the two methods that frontier wisdom had always recommended: log construction, where timber could be found, or sod houses where it could not. The Gunderson family, whose claim lay 3 miles south of what would become Jonah Miller's homestead, had spent their first summer cutting sod blocks from the creek bottom, stacking them like giant bricks to form walls 3 feet thick. The work was backbreaking, each block weighing 40 pounds when wet, and the finished house looked solid enough to last generations. The reality proved different. The sandy soil of the upland sandhills lacked the dense root structure that made prairie sod stable in other regions. By their second winter, the Gundersons watched their walls settle unevenly, gaps opening along the corners where wind drove snow into their kitchen. The south wall developed a lean that worsened each spring as frost heaved the foundation and summer heat dried the sod blocks into crumbling earth. Mrs. Gunderson spent hours each week rechinking the gaps with fresh mud, fighting a losing battle against walls that wanted to return to the prairie they came from. Those settlers with money or connections tried importing lumber, but the costs proved crushing. The Holbrook brothers had hauled enough pine boards from Grand Island to frame a proper house, spending nearly $200 on materials alone before counting the weeks of wagon trips required to move it all. Their finished home was tight and square, built to patterns any carpenter back east would recognize, but the thin walls and single-layer board construction offered little protection against prairie winds that could drop temperatures 30 degrees in an hour. The Holbrooks burned 6 cords of wood their first winter, hauling cottonwood from creek beds and buying coal from town when they could afford it. Even so, their children slept in wool coats on the coldest nights, and ice regularly formed on the inside of their windows, despite a fire burning constantly in the kitchen stove. The house was everything frontier building guides said it should be, yet it failed to provide the basic comfort any family needed to survive Nebraska winters. These failures were not unique to the Sandhills. Across the Great Plains, homesteaders struggled with the same fundamental problem. Building methods developed in forested regions simply did not work in grassland environments. Traditional log construction required trees that did not exist. Sod building demanded soil conditions that varied wildly from place to place, and imported lumber created costs that could bankrupt a farming family before their first harvest. Into this environment came Jonah Miller in the spring of 1899, a man whose background positioned him to see possibilities that others missed. He had grown up on a grain farm in southeastern Pennsylvania, where his father and grandfather had managed hay operations that fed dairy cattle through long winters. The Miller farm had included a massive barn built by German immigrants in the 1750s, its walls filled with loose straw between heavy timber posts, the whole structure designed to store enormous quantities of hay while keeping it dry through months of cold weather. Jonah had spent his youth learning the properties of hay and straw, understanding how different grasses behaved when cut, dried, baled, and stored. He knew that wheat straw, when properly cured, could last for years without rotting if kept away from ground moisture. He had seen how loose straw in barn walls created insulation that kept livestock comfortable even when outside temperatures dropped well below zero. Most importantly, he had watched the new mechanical hay balers that appeared in Pennsylvania during the 1880s, machines that compressed loose hay into tight, rectangular blocks that could be stacked like building stones. When Jonah surveyed his sandhills claimed that first spring, he saw what every other settler saw: endless grass, sandy soil, scattered timber, and the challenge of creating shelter from materials that seemed inadequate for permanent construction. But his Pennsylvania experience also showed him something others missed. The prairie grass that locals cut for hay produced bales that were uniform in size, tightly compressed, and available in quantities that dwarfed the lumber supply from the nearest sawmill. The idea came to him gradually, not as sudden inspiration, but as logical extension of what he already knew about straw and insulation. If German barn builders could create warm, stable walls using loose straw between posts, why could not compressed bales serve the same function more efficiently? If Pennsylvania farmers could store tons of baled hay in structures that lasted decades, why could not those same bales become the structure itself? The first time Jonah mentioned the possibility to his nearest neighbors, the response was immediate and dismissive. Tom Brennan, whose family had been fighting their sod house for 3 years, laughed out loud at the suggestion. "That is barn thinking, Miller. You want to live like livestock? You go ahead, but do not expect any of us to follow you into that foolishness." Sarah Holbrook was more direct. "Straw is what you put under animals. People live in real houses made of real materials. Wood and stone have kept families alive for centuries. Grass will not." The skepticism ran deeper than simple conservatism. These were people whose survival depended on making sound decisions about shelter, and they had no patience for experiments that might fail when winter winds started blowing. They had seen what happened to families whose houses collapsed or burned, or simply proved inadequate when the weather turned harsh. The stakes were too high for innovation that had not been proven by generations of use. But Jonah Miller had seen those generations of use, just in a different context. He began planning his experiment. The first test came not from wind or cold, but from water. Spring rains in the sandhills arrived unpredictably, turning sandy creek beds into rushing torrents and pooling in low spots where winter snow had lingered. Jonah Miller watched the water table rise and fall with the weather, noting how moisture moved through the loose soil that made this region both easy to work and treacherous to build upon. His Pennsylvania upbringing had taught him that water was the enemy of any structure, but especially one built from organic materials. His grandfather's stone foundation barn had lasted nearly 150 years because German builders understood a fundamental principle: keep wood and straw away from ground moisture, and they would outlast the families that built with them. Let them touch damp earth, and rot would destroy the strongest timbers within a decade. The lesson became urgent when Jonah examined what remained of earlier settlers' attempts at unconventional building. 3 miles northwest, he found the remnants of a hay storage shed that Otto Kreminski had built the previous autumn. Kreminski had stacked loose hay directly on the ground, covering it with canvas and hoping for the best. Spring moisture had wicked up through the bottom layers, creating a perfect environment for decay. By May, the entire bottom course of hay had turned into black, soggy compost that attracted mice and gave off the sweet smell of fermentation. This failure pointed toward a solution. If ground contact destroyed organic building materials, then elevation became essential. But elevation alone was not enough. The sandy sandhill soil presented unique challenges that required techniques adapted specifically to local conditions. Jonah began by studying the water patterns around his chosen building site. He selected a gentle rise that would naturally shed rainwater, avoiding both the low spots that collected moisture and the exposed ridges that took the full force of prairie winds. Then he began digging, not for a basement, but for a foundation system that would break the connection between his future bale walls and the earth below. The foundation trenches went down 3 feet, following the outline of his planned house, with extensions at each corner. Into these trenches he placed a layer of creek gravel, carefully sorted stones ranging from egg-size down to coarse sand. This gravel bed would serve as more than simple support. It would act as a drainage medium that could absorb and channel water away from the structure above. On top of the gravel, Jonah laid flat limestone blocks that he hauled from outcroppings along the Middle Loop River, 20 miles to the east. Each stone was roughly 18 inches wide and 8 inches thick, creating a level platform that rose 15 inches above the surrounding ground level. The limestone served a dual purpose. It provided a stable base for wall construction, and its porous nature allowed moisture to evaporate rather than accumulating beneath the building materials. The critical innovation came in the moisture barrier system. Jonah had watched too many frontier buildings fail because builders assumed that solid materials would naturally resist water infiltration. Instead, he created what Pennsylvania barn builders called a breaking layer, a deliberate interruption in the capillary action that could draw moisture from soil into organic materials above. On top of each limestone block, he placed a thick oak plank that had been coated with pine tar and sealed at the ends. These planks, each 2 inches thick and 8 inches wide, formed a continuous sill that would support the bottom course of bales while preventing any direct contact between straw and stone. The tar coating was essential. It created a waterproof barrier that moisture could not cross, even if it managed to work its way up through the gravel and limestone layers. The drainage system extended beyond the foundation itself. Jonah dug shallow trenches radiating outward from each side of the house, creating channels that would carry rainwater away from the building site before it could pool against the foundation walls. These trenches followed the natural slope of the land, dropping 1 inch for every 10 feet of length to ensure positive drainage even during the heaviest spring storms. The trenches themselves were filled with smaller gravel and topped with sod, creating what looked like natural swales but functioned as an engineered water management system. During heavy rains, water would flow into these channels and away from the building site, rather than collecting around the foundation where it could eventually work its way into the structure above. This approach reflected knowledge that Jonah had absorbed during childhood visits to his great-uncle's mill in Lancaster County. The mill foundation had been built by Moravian craftsmen in the early 1800s, using techniques that kept the wooden machinery dry even when the mill race was running at full capacity just 20 feet away. The key was understanding water as a force that could be directed and managed, rather than simply resisted. When Tom Brennan stopped by in June to watch the foundation work, his skepticism was evident. "You are building a stone castle for a hay house, Miller. All that digging and hauling, you could have framed a proper cabin with less work." But Jonah had calculated differently. The stone and gravel had cost him only labor and the rental of a wagon for the limestone hauls. A comparable foundation using imported materials would have required hundreds of board feet of treated lumber at prices that could consume a homesteader's entire first-year budget. More importantly, Jonah was building for conditions that his neighbors had not fully grasped. The sandhills presented a specific combination of challenges: sandy soil that drained quickly but also shifted unpredictably, temperature swings that could crack rigid foundations, and moisture patterns that varied dramatically between wet springs and dry summers. His elevated stone foundation system was designed to handle all of these variables while providing a stable platform for the experimental wall system he planned to build above. The real test came in early July, when a 3-day storm dumped nearly 4 inches of rain across the region. Water poured off the foundation stones and flowed smoothly through the drainage channels, leaving no standing water within 50 feet of the building site. Meanwhile, the Holbrook family spent 2 days bailing water from their wood-framed house, where inadequate foundation drainage had allowed runoff to collect against the walls and seep through gaps in the floorboards. When the storm passed, Jonah measured moisture levels in his foundation stones using the simple test his grandfather had taught him, placing dry wood shavings against the stone surface and checking for dampness after 24 hours. The limestone blocks showed no sign of retained moisture, while the gravel bed had drained completely within 6 hours of the rain stopping. The foundation system was ready to support whatever Jonah planned to build above it. More importantly, it had already proven that water could be managed through design rather than simply endured as an inevitable hazard. The techniques were not revolutionary, but their application to bale construction represented a crucial step toward making his experiment viable for long-term habitation. The bales arrived in August, delivered by wagon from Heinrich Zimmermann's farm 6 miles south, where a new mechanical baler had been turning prairie grass into compressed rectangular blocks since early summer. Each bale measured 18 inches high, 14 inches wide, and 36 inches long, weighing approximately 40 pounds when properly cured. Jonah had ordered 50 bales initially, intending to test the stacking and handling characteristics before committing to full wall construction. The first challenge was achieving level courses without the uniform dimensions that sawn lumber provided. Unlike manufactured materials, each bale varied slightly in density and exact measurements, requiring constant adjustment to maintain plumb walls. Jonah developed a technique using wooden wedges driven between bales to eliminate gaps and ensure tight joints. Where bales were slightly undersized, he packed loose straw into the voids, compressing it by hand until the wall surface remained flat and solid. The stacking pattern followed masonry principles that Jonah had observed in Pennsylvania stone construction. Each bale was laid like a brick, with vertical joints offset from the course below, creating interlocking strength that prevented the walls from separating under lateral stress. The bottom course sat directly on the tar-coated sill planks, with each subsequent layer pressed firmly against the one below until the walls reached 8 courses high, creating a finished wall thickness of 12 feet. But thickness alone did not guarantee thermal performance. The crucial factor was air movement within the wall system. Jonah had learned from his grandfather that dead air was nature's most effective insulator, but only when it remained truly still. Moving air carried heat away through convection, turning potential insulation into a thermal drain. The key was creating sealed air pockets that could not participate in heat transfer. This principle guided the plastering process that began in September. Jonah mixed local clay with chopped straw and water, creating a thick mud plaster that could be worked into every gap and surface irregularity of the bale walls. The plaster served multiple functions. It sealed the straw against air infiltration, created a smooth surface for interior finishing, and added structural cohesion that transformed loose agricultural waste into a solid building system. The exterior plaster was applied in 2 coats, each approximately 1 inch thick. The first coat was worked deep into the surface texture of the bales, filling every void and creating an airtight barrier. After this base coat dried for 1 week, Jonah applied the finish coat mixed with lime that he had burned from shells collected along the Platte River. The lime plaster created a hard, weather-resistant surface that would shed rain while allowing moisture vapor to escape from within the wall system. Interior plastering followed the same 2-coat process, but with different materials chosen for their performance in heated indoor conditions. The base coat used the same clay and straw mixture, but the finish coat incorporated fine sand and additional lime to create a smooth, light-colored surface that would reflect lamplight and resist the soot accumulation that plagued many frontier homes during long winter evenings. The thermal testing began naturally as autumn temperatures started dropping in October. Jonah built small fires in his kitchen stove, measuring fuel consumption and interior temperatures using methods his father had taught him for monitoring barn conditions during Pennsylvania winters. A simple thermometer hung on the north wall, away from direct heat sources, while another thermometer outside the north window recorded ambient air temperature. The results exceeded his calculations. On a night when outside temperatures dropped to 20 degrees Fahrenheit, the interior temperature stabilized at 58 degrees with only a modest fire burning in the kitchen stove. By comparison, the Holbrook family reported interior temperatures of 32 degrees the same night, despite burning a larger fire continuously through the evening hours. More significantly, the bale house retained heat long after the fire died down. When Jonah allowed his stove to burn out completely at bedtime, The interior temperature dropped only 8 degrees by morning, while outside temperatures fell another 12 degrees before dawn. The thermal mass effect of the thick walls was storing heat during active burning periods and releasing it slowly throughout the night, maintaining comfortable conditions with minimal fuel input. The fuel economy became apparent through precise measurement. During a typical week in November, with daytime temperatures ranging from 30 to 45 degrees and nighttime lows between 15 and 25 degrees, Jonah burned 1/4 cord of cottonwood to maintain interior temperatures above 50 degrees. The Holbrook family, heating a comparable floor area in their frame house, consumed 1 full cord during the same period while achieving lower average interior temperatures. This performance differential reflected the fundamental physics of heat transfer through different wall systems. The 12-inch bale walls created an insulation barrier that slowed conductive heat loss, while the sealed air spaces within the straw eliminated convective heat transfer that plagued structures built with gaps and air leaks. The thick walls also provided thermal mass that moderated temperature swings, preventing the rapid heat loss that occurred in thin-walled buildings as soon as heating sources were reduced. Word of these results spread through informal networks that connected scattered homesteads across the region. Martha Brennan mentioned to Sarah Holbrook that the Miller family seemed unusually comfortable during the cold snap in late November. Tom Brennan admitted that he had stopped by Jonah's place during a blizzard and found the interior warm enough for shirt-sleeve comfort, with no fire visible in the stove. The skepticism began shifting toward curiosity as winter deepened and fuel costs mounted for families using conventional construction. Coal delivered from Grand Island cost $2 per ton, while cottonwood cut from creek bottoms required days of labor that could have been spent on other essential tasks. The Miller family's fuel efficiency represented real savings that could determine whether a homesteading family survived their first winter with resources intact for spring planting. By December, several neighbors had visited to examine the bale construction more closely. They found walls that felt solid when knocked upon, surfaces that showed no signs of settling or deterioration, and interior conditions that remained comfortable even when outside winds drove snow against the windows. The experimental building had become a functional demonstration that challenged assumptions about what materials could provide adequate shelter on the Great Plains. The thermal performance data was accumulating into a compelling case for techniques that used abundant local materials to achieve superior results with less labor and expense than conventional methods required. But the ultimate test was yet to come, when the full force of prairie winter would determine whether innovation could withstand the conditions that had defeated so many families attempting to establish permanent homes in this unforgiving landscape. The roof system presented challenges that no frontier building manual had ever addressed. Conventional wisdom assumed that walls were either solid timber capable of bearing enormous loads or stone masonry that could support virtually any roof design. Bale walls fell into neither category, requiring structural solutions that distributed weight evenly while accounting for the compressed organic nature of the supporting material beneath. Jonah had observed roof failures throughout the Sandhills during his first 2 years of residency. The Gunderson family's sod house had developed a dangerous sag along the ridge beam when snow accumulated in February, while the Kreminski cabin had lost an entire section of shingles during a spring windstorm that caught the extended eaves and twisted the roof structure beyond its connection capacity. Both failures resulted from fundamental misunderstanding of how loads moved through different building systems. Traditional gable roof construction concentrated the entire roof load on 2 opposing walls, with the ridge beam transferring weight down through the end walls to the foundation. This approach worked adequately when walls were thick logs or stone that could bear concentrated loads without deformation. But bale walls, despite their thermal excellence, could compress underpoint loads or buckle if stressed unevenly along their length. The solution came from studying barn construction techniques that Jonah had observed during his Pennsylvania childhood. German immigrants in Lancaster County built massive hay storage barns using hip roof designs that distributed loads across all 4 walls rather than concentrating stress on 2 gable ends. These barns carried enormous weights of stored hay and equipment while maintaining structural stability for decades without major repairs. Adapting this principle to residential construction required careful attention to load path engineering. Instead of a ridge beam running between 2 end walls, Jonah designed a hip roof system with four triangular roof sections meeting at a central point. This configuration transferred roof loads down through rafters that bore against all four walls simultaneously, spreading the weight evenly across the entire perimeter of the building. The critical structural element was the top plate system that crowned the bale walls. Jonah selected straight-grained oak planks, each 4 inches wide and 2 inches thick, running continuously around the entire perimeter of the building. These planks were notched at the corners and secured with wooden pegs driven through overlapping joints, creating a rigid ring that could distribute loads laterally while preventing the walls from spreading under roof weight. Each roof rafter was cut to bear directly against this top plate, with the lower end of each rafter notched to sit firmly against the oak plank. The rafters themselves were spaced 24 inches on center, closer than typical frontier construction, but necessary to prevent any single rafter from applying concentrated loads that might compress the bales beneath. This spacing also provided adequate support for the board sheathing that would carry the final roofing material. The hip design required careful calculation of rafter angles and lengths. Each rafter met the top plate at a 30-degree angle, creating a roof slope steep enough to shed water quickly while remaining low enough to minimize wind resistance. The 4 hip rafters that formed the corners of the roof required compound angles that Jonah cut using templates carved from scrap wood, ensuring identical geometry for each corner. Wind resistance became a primary concern as construction progressed through October. The Sandhills region experienced frequent high winds that could generate enormous uplift forces on roofing systems, particularly those with large overhangs or steep slopes that caught wind like sails. Conventional cabin construction often failed when wind forces exceeded the holding power of nails or pegs connecting the roof to the walls below. Jonah minimized wind vulnerability by keeping roof overhangs to 6 inches on all sides, just enough to direct rainwater away from the walls while avoiding the leverage that larger overhangs created during windstorms. The hip configuration also reduced wind resistance by eliminating the large flat surfaces of gable ends that could catch crosswinds and create destructive stress concentrations. The roof-to-wall connection system used techniques adapted from shipbuilding that Jonah had learned from his uncle, a carpenter who had worked in Philadelphia shipyards before moving inland to farm. Each rafter was secured to the top plate with both a notched bearing joint and a wooden peg driven at an angle through the rafter and into the oak plank below. This dual connection prevented both uplift and lateral movement, creating a mechanical bond that could resist wind forces from any direction. Board sheathing was applied diagonally across the rafters, with each board running from the top plate on one side to the peak connection on the opposite side. This diagonal pattern created triangulated strength that prevented the roof structure from racking under wind loads, while providing a solid base for the final cedar shingle layer. The boards were secured with square-cut nails driven into pre-drilled holes to prevent splitting. The first test of the structural system came during a November windstorm that brought sustained winds of 40 miles per hour, with gusts exceeding 60 miles per hour. The storm struck at night, waking families across the region with the sound of loose objects being hurled against buildings and the groaning of structures under stress. At the Holbrook place, the wind caught the extended eaves of their gable roof and twisted the entire structure, pulling several rafters loose from their connection points and allowing the northwest corner of the roof to lift and slam repeatedly against the remaining structure. Tom Brennan spent the storm holding interior doors closed against wind pressure that had found gaps in his sod house walls, while outside his roof lost 12 shingles that scattered across the prairie. The bale house weathered the storm without structural movement. Jonah checked the building repeatedly throughout the night, finding no sign of stress or displacement in any part of the roof system. The hip design shed wind from all directions, while the continuous top plate distributed the loads evenly across walls that remained plumb and solid. When morning came, the structure showed no damage beyond a few shingles that required minor repositioning. More importantly, the walls themselves had proven capable of supporting structural loads without the compression or buckling that skeptics had predicted. The top plate system had successfully transferred roof loads into the bale walls, while maintaining the thermal integrity that made the building system viable. The compressed straw had behaved like solid masonry under load, demonstrating that organic materials could provide structural strength when properly configured and supported. By December, the completed building had demonstrated that unconventional materials could achieve structural performance equal to conventional construction while providing superior thermal efficiency and using locally available resources. The integration of foundation, wall, and roof systems had created a unified structure that responded to environmental stresses as a coherent unit rather than a collection of separate components fighting against each other. The winter of 1902 arrived early and stayed late, bringing the kind of sustained cold that separated successful homesteaders from those who abandoned their claims and retreated to towns. By January 15th, temperatures had remained below 0 degrees Fahrenheit for 18 consecutive days, with nighttime readings dropping as low as 28 degrees below zero. Snow fell almost daily, creating drifts that reached the eaves of single-story buildings and making travel between homesteads nearly impossible for weeks at a time. This was the test that revealed the full integration of Jonah Miller's building system. While individual components had proven themselves during milder weather, the extreme conditions of this winter demanded that foundation, walls, and roof work together as a unified thermal envelope capable of maintaining human habitation under conditions that pushed conventional structures beyond their limits. The continuous cold created thermal stresses that exposed weaknesses in buildings throughout the region. At the Holbrook Place, repeated freeze-thaw cycles opened new gaps between wall boards as the wood contracted and expanded, while frost buildup on interior walls indicated that heated air was escaping through joints that had seemed tight during construction. The Gunderson sod house developed ice formations along the base of interior walls, where ground frost penetrated the inadequate foundation system, creating conditions that made the lower portions of their single room uninhabitable. But the sustained cold also revealed the thermal flywheel effect that made Jonah's thick-walled system superior to conventional construction under extreme conditions. The massive bale walls stored heat during the brief periods when the stove burned actively, then released that stored energy slowly over many hours, maintaining interior temperatures even when fuel supplies ran low or families slept through the night without tending fires. This thermal inertia became crucial during a 10-day period in late January, when blizzard conditions made it impossible to venture outside for additional firewood. Families across the region were forced to ration their remaining fuel supplies, while hoping that weather conditions would moderate enough to allow resupply trips to distant timber sources. The Brennan family burned furniture and interior walls torn from their sod house to maintain minimal heat, while still suffering interior temperatures that dropped into the teens during the coldest nights. The Miller family faced the same fuel shortage with dramatically different results. Starting the crisis period with only 2 days' worth of normal fuel consumption remaining, they reduced their stove firing to one brief period at midday and another before bedtime. Even with this severe reduction, the interior temperature never dropped below 42 degrees Fahrenheit, warm enough to prevent water from freezing and maintain conditions suitable for normal household activities, including cooking and basic washing. The performance differential became measurable through direct comparison with the Holbrook family, whose frame house occupied a similar-sized footprint on comparable terrain just 2 miles away. During the coldest week of February, with outside temperatures averaging 15 degrees below zero, the Holbrooks maintained an average interior temperature of 28 degrees while burning 1 1/2 cords of cottonwood. The Miller family achieved an average interior temperature of 51 degrees while consuming only 1/2 cord of the same fuel type. These results reflected the compound advantages of proper building system integration. The elevated stone foundation prevented ground frost from conducting cold into the floor area, while the thick walls reduced heat loss through conduction and convection. The hip roof design eliminated the thermal bridging that occurred where gable end rafters penetrated conventional wall systems, and the continuous top plate prevented air infiltration at the critical wall-to-roof junction. More significantly, the building maintained its thermal performance without degradation over time. Many frontier structures showed declining efficiency as gaps opened, joints loosened, and materials settled or shifted. The Bale House demonstrated improved performance during its second winter as the compressed straw continued settling into tighter configurations, while the lime plaster cured to increased hardness and weather resistance. Word of these results reached families throughout the region through the informal communication networks that connected isolated homesteads during long winter months. When travel became possible again in March, several neighbors made specific trips to examine the Miller house and discuss construction techniques that had achieved such remarkable fuel efficiency under extreme conditions. The first serious inquirer was Heinrich Zimmermann, the farmer who had supplied the original bales and had watched the construction process with skeptical interest. After spending an evening in the warm interior while outside temperatures remained below freezing, Zimmermann asked detailed questions about foundation preparation, wall construction sequence, and plastering techniques. By April, he had begun construction of his own bale house, modifying Jonah's design to include a larger kitchen and additional windows while maintaining the essential thermal and structural principles. The adoption process accelerated when the local Lutheran congregation decided to construct a new church building in 1904. Faced with the high cost of importing sufficient lumber for conventional frame construction, the building committee invited Jonah to present his bale building methods as a potential alternative. The resulting church building used load-bearing bale walls 2½ feet thick, creating a worship space that could be heated comfortably with a single wood stove even during the coldest Sunday services. This church construction project, completed in 1905 and used continuously for over 20 years, demonstrated that bale building techniques could produce structures suitable for public use and capable of long-term durability. The building required only routine maintenance consisting of annual lime wash applications to the exterior plaster and occasional replacement of damaged shingles, costs that remained far below those associated with frame construction of comparable size. By 1910, at least 12 bale houses had been constructed in the immediate region, with the techniques spreading to other areas of the Sandhills, as homesteaders shared information about materials and methods that could provide comfortable shelter using locally available resources. The practical advantages of reduced fuel consumption, lower construction costs, and improved comfort levels during extreme weather had overcome the initial skepticism about using agricultural waste products for permanent construction. The broader significance of this innovation extended beyond individual building projects. The successful adaptation of organic materials to structural use demonstrated that frontier families could achieve housing standards comparable to those in more developed regions without depending on expensive imported materials or specialized craftsmen. The techniques required only basic carpentry skills and tools that most homesteaders already possessed, making improved housing accessible to families operating on limited budgets. The integration of traditional building knowledge with locally available materials had created a sustainable approach to shelter that worked within the environmental and economic constraints of Great Plains settlement. The method succeeded because it addressed the specific challenges of the region, rather than attempting to impose construction techniques developed for different climates and resource bases.